Hi, I'm Lakshadip and I will be presenting our work on multi-view object pose distribution tracking for pre-graph planning on mobile robots. So today, mobile manipulation is often solved using a sequential approach. That is, robot first navigates near the table with all the objects, then it observes these objects and estimates their 60 pose. Based on this, it plans the grasp and finally it executes the grasp. So such an approach has two major limitations. First of all, it doesn't take into account the success of the grasping task. That is, can the uncertainties in the pose estimate of the object be compensated using the robot's gripper? And second, it is inefficient as it treats navigation and manipulation as two separate problems. So in this work, instead of just estimating a 60 pose of the object, we try to estimate the full 60 object pose distribution. That is the 60 object pose estimate along with the uncertainty. We also track this pose distribution when the robot is still very far from the object or it is still navigating towards the object. And in this way, robot can get a very early estimate of this uncertainties in the object pose estimates. And based on that, it can either take an action to reduce its uncertainty or it can already start planning the grasping task. And our work is based on the Rao localized particle filter, which was proposed by Deng et al. In their paper Pose RBPF. So we have extended it to fuse information from the external cameras in addition to the robot camera. So by this, we compensate for the limited view of the robot camera. Further, we model the translation as well as the orientation distribution of the object pose estimate as the multimodal distributions. And in this way, we can compensate for the large distance between the object and the robot camera when the robot is still navigating towards the object, and also the occlusions from the other objects. So this is our proposed architecture. So we start with the particles that are coming from different camera frames. Then we apply the motion model. Then based on the transformations between the different cameras, we predict where the object will appear in different camera frames. And then this cropped images are passed to the autoencoder. So this autoencoder generates code for each particle in different frames. And then these codes are compared with the code book that is generated offline, wherein we have the codes for all possible orientations of the objects. So we compare these codes with the codes we have generated now, and with this we get an orientation likelihood for that particle in each camera frame, and then we fuse them to have a resultant orientation distribution. Then we weigh these particles, and then we do the resampling and promote the particles that have the higher weights. So for the experimental evaluation, we use the simulated YCB dataset, which contains 8 different YCB objects, and they were created using a photorealistic renderer. And each of these sequence has views from the robot camera, wherein the robot is moving towards the object. And in addition to that, we also have the views from the external cameras, which are stationary. So now let's see some qualitative results. Yeah, in case of multi-view, the errors as well as the uncertainties converge quite quickly, even when the object is very far from the robot. And in case of a single view, it takes some time before it starts to converge. And another thing to notice here is that when we are very close to the object, single view actually has much smaller error compared to the multi-view. So to conclude, by using the information from external stationary cameras, we can have much faster convergence of translation and orientation errors along with the uncertainties compared to the single view baseline for the given problem. Further, when the robot camera has a very good view of the object, single view actually results in much better estimates compared to the multi-view. This is because the camera are very far from the object, so they actually end up introducing noise, and that's why we get a bad estimates. And our current work is looking more into how we should determine when to use the information from external cameras and when not. And also, because we have a moving robot camera here, we always have the possibility to plan the views of this camera so that we can reduce this uncertainty. And that is something we are also looking into. So thank you for your attention.